Hello and welcome back again to Physixify. Today we are talking about work energy theorem. You can see this car that moves, it carries some energy. Does it? Let's talk about it. So, first thing is, what is kinetic energy? If you want to define kinetic energy, you say that this is the energy due to motion. Anything that is moving, जो भी चीज चल रही होगी वो आपके पास काइनेटिक एनर्जी रखेगी, राइट? इफ यू सी दिस कार, आपके पास ये कार जो चल के आई है, आई होप यू कैन से दैट दिस इज हैविंग अ काइनेटिक एनर्जी. नाउ इफ दिस इज मूविंग, अगर ये चल रहा है तो इट ऑल्सो हैज अ स्पीड, राइट? काइनेटिक एनर्जी जो हमारी क्वांटिटी है, दिस वुड बी अ स्केलर क्वांटिटी. तो प्लीज रिमेंबर, दिस इज वन इंपॉर्टेंट फैक्ट दैट दिस इज सेम लाइक वर्क. Scalar quantity, something that does not have direction. Next thing in this happens to be the formula, that is half mv square. Most of you would know it from previous probable lessons that kinetic energy half mv square, m is the mass, v is the speed. So let's talk a little more about that. Now, what we are saying is, what does exactly kinetic energy depend upon? Right? You have this car, you can say that it does depend on the mass. Let us say the mass is given. This is 500 kg for the car. It also depends on speed and not velocity. It's very important to see that it is not depending on velocity, but it actually depends on the speed. So I might assume that it is moving with 50 km per hour. I can say that if I want to write the kinetic energy, this K would be given as half into mass, that is 500 into 50 square. This would give me energy in kg and kilometer per hour square being the units. It won't be the SI unit, but at least I can get the kinetic energy in some terms over here. The next thing over here would be the frame of reference. This is one thing which is very important, because in different frame of references you see different speeds. So similarly your kinetic energy might change. Now, the next thing I would like to show you this dependence. So if I consider a stone and I throw it in three ways. The first way is A, I am throwing it with 5 meter per second in a certain direction. You can see over here. Similarly, B, I'm throwing it in some other direction. You can see it over here. And C, with again 5 meter per second in a different direction altogether. So in all the cases, one thing that I can say is work done would be same. In A, in B, in C, in all the cases it would be same, because the mass is same and the speed is same. If, let us say, I want to talk about the frame of reference, and let us say there is this guy who's sitting on the car and comes with the car, what will he say? He will say that to me the car is in rest. The speed of car is 0 to me, and that's why I will say that there is no kinetic energy, or you can say zero kinetic energy with respect to the guy sitting on the car. But if I talk about this person who was standing, let us say at rest outside, what will he say? He will say that for me the car is in motion, and that means it has a non-zero kinetic energy, which means that it has some kinetic energy. We don't want to go into the details how much, because we are just learning if kinetic energy is there or not. Now, if I move on later, I'll just say that this is one important result for you to remember, that kinetic energy does depend on the frame of reference. Moving ahead, we can state the work energy theorem now. And what does this say? It says that work done by all the forces combined equals the change in kinetic energy. Now, you might be tending to ask, sir, what do you mean by all forces? I will say all means all. If Amitabh Bachchan said no means no, I will say all forces means all forces, and that means every type of force. If I want to take it in part 1, I would say both internal and external force. That is one part of all forces. And similarly, the one that we studied in the previous videos, that is conservative and non-conservative, comes in part 2. So you can say all types of forces, internal, external, conservative, non-conservative, all four combined, you take the work done with all these forces, that would be equal to the change in kinetic energy. Now, one common thing that a lot of people ask is that if the work done is on the body, what will happen? And if work done is by the body, what will happen? Things change significantly if you talk with respect to physics and with respect to chemistry. So with respect to physics, we are saying that work done on the body means that we are giving energy to the body. The work done is positive, and that means the kinetic energy will increase. But if you talk about work is done by the body, you will say that in this case, work done is less than 0, it is negative, and the kinetic energy is bound to decrease. So this was something regarding work energy theorem with respect to the blabber, with respect to the statements, with respect to English, with respect to just what we want to convey as our feelings. Is there any mathematics involved? Yes, there is. Let's talk about that. So we have the proof of work energy theorem. First of all, we are going to give the statement. The statement says that work done by all the forces, that is the conservative force, the non-conservative force, the internal force, the external force, equals the change in kinetic energy. Now, if I want to prove this up, what will I do? First of all, I will say that what effectively I want to say is, this is the statement in a more effective manner. That work done by all the forces equals change in kinetic energy, that is kinetic energy final minus kinetic energy initial. I can say this in another way, that if I differentiate on both the sides, I'll get dW by all the forces equal to differentiation of kinetic energy. Now what I can say is that if I integrate all the small work done, I can get my full work done by all the forces, which will turn out to be change in kinetic energy. You don't believe me? I hope you will after you see this statement, right? If I want to get my full work done, first of all, I am trying to integrate my all the small work done f dx from x1 to x2. Next thing I can say, the net force will be equal to ma. As soon as I write ma dot dx, I can put a as v dv by dx. This comes in from the kinematics part. I hope you remember a can be written as dv by dt, a can also be written as v dv by dx if you want to write it in terms of v and x. Later on you see dx and dx cancel out, this would be mv dv, and you can say that if at x1 velocity is vi, if at x2 your final velocity is vf, you will get m integral v dv from vi to vf, and on integrating it would simply yield half mvf square minus half mvi square, which is actually final kinetic energy minus initial. So here is the proof of work energy theorem. I hope that you understood whatever was to be told in the work energy theorem. We'll talk about numericals in the next class, but if you did like this video, please make sure you like it up, and if you want to never miss a new video, do hit the subscribe button. And if you want to get in touch with me, there's a Telegram group, there's a Instagram group. The link is in the description. You can check it out and you can get added over there as well. If you had any problems with respect to this video, please make sure you drop your queries, your doubts in the comment box. This is me saying hasta la vista. Bye bye.